are doing well, your days are going productive, and you are doing excellent in your studies. So let's dive into the next part of quantum, which we were discussing. So a brief recap. We have seen the basic history, basic mathematics, and we were just learning function and operator, and we were reading the properties of an operator. And we have seen various properties, and in them, one property says that to every observable in classical mechanics, there exists an operator in quantum mechanics. Okay. Now, one by one, we were looking at the few observables and their quantum mechanical mathematical operator. We were discussing that. In that context, first we have discussed the position, next linear momentum, then kinetic energy, then potential energy, then total energy. And in total energy, finally we have seen the Hamiltonian operator. This was our last discussion. So we introduced a sign which looks like inverted triangle, and I have said that it is called Laplace. It is a common use term. What it is called Laplacian operator, this one. Now, what this means? This actually means ddx. Actually, if you study vector in higher mathematics, you will see that this means I cap plus ddx j cap plus ddy j cap plus ddz k cap. Now, suppose we are taking one dimension, then Laplace square becomes, I am just the new lecture, so I am taking a different slide. So we have seen one operator, that is Laplace. In one direction, I am calling it del x, and without the sign, as I am not mentioning the direction, that's why I am not putting I cap or j cap or k cap here. So Laplace square will be del 2 del x2, right? Because it is an Laplacian operator, and in operator there is a multiplicative property. I have said you, because one operator operates to the next operator. Okay, Laplace square. Now, if my particle is moving along one direction only, then this will be the Laplace square. But if my particle moves in two dimension, then the Laplace square becomes like this: del 2 del x2 plus del 2 del y2. This is basically our Laplacian operator becomes. Okay, no issues. So this is when my particle moves in two dimension, in two direction. So similarly, my Laplace square will be del 2 del x2 plus del 2 del y2 plus del 2 del z2 when my particle is moving along three direction. So this is for one dimension, this is for two dimensional movement, and this is for three dimensional movement. Okay, so this is our Laplacian operator. Now we have discussed, till now we have discussed 5 observable of classical mechanics, and their corresponding quantum mechanical operator. 5: position, linear momentum, kinetic energy, potential energy, and with its addition, total energy, right? Now let's dive into one of the most complicated one, which is angular momentum. So sixth number we are going to look at, which is angular momentum. So just write in this way: sixth angular momentum. Now what is angular momentum? Momentum, linear momentum means m into v, mass into velocity, right? But angular momentum means it is denoted by capital L, and it is multiplication of, suppose a particle is moving in a circular motion. At any point it will have direction of motion like this, and in this direction it will have a linear momentum, and another force will be acting towards the center. So the distance from center to that particle is basically r. Angular momentum is r cross p, linear momentum vector into radius vector. Okay, now suppose the particle is moving along 3 dimension. Suppose I have drawn here a circle, imagine it is a sphere, okay, and particle is moving along 3 dimension. Then how can we write this angular momentum? Because I have written just here, I have not mentioned any direction, so by default it indicates 1 dimension, right? But to understand the true nature of the particle, we need to encounter 3 dimension. So in 3 dimension, position of a particle can be denoted by some value. In Cartesian coordinate you write like this, 1, 3, 5, this is a location of this. But in vector you write it like this, x I cap plus y j cap plus z k cap. Okay, vector L you write in like this, Lx, because in classical mechanics the thing denotes position. In quantum mechanics this will become an operator, that's why I have put operator sign on it. Okay, x cap, this cap indicates it's an operator, but this cap, it's just I cap, j cap, k cap, these are basically phenomena of vector. Okay, in vector we denote the x coordinate with I cap, y coordinate, j cap, like that. You have, I hope you have studied in your 11, 12. So Lx I cap plus Ly j cap plus Lz k cap. That means the x direction, x component, y component and z component of angular momentum, right? Lx, Ly, Lz are the x, y and z component of angular momentum. Now what will be P? P will be definitely Px I cap plus Py j cap plus Pz k cap, right? Simple. Similarly, if we want to write what will be r square, r cap square, that will be x cap square plus y cap square plus z cap square, because I cap, if it is the absolute value, when we take its square then this I cap, j cap, k cap vanishes, so only numerical value remains. Okay, this is a mathematical phenomena of vector. If you square a term, the I cap, j cap, k cap has no value, no meaning at all, because you are removing the directional nature, right? For example, -1 or +1, this is directional, but if you put it square, then it will be 1 without a direction. Now L square, similarly Lx square plus Ly square plus Lz square, P square equal to Px plus Py plus Pz all are square and with operator sign. No issues at all. Now we have to write this, right? L. Now Look very carefully. We know L equal to R cross P, right? L equal to R cross P. Now, for getting absolute value, we have to multiply R this, and we will get this, isn't it? So we can write Lx I cap plus Ly j cap plus Lz k cap. Now you need to understand vector a little bit. When two vector quantity you multiply it in this way. First you write I cap, j cap, k cap, and then you write R. So first you will write the I cap, j cap, coefficient of I cap, j cap, k cap corresponding to R. Corresponding to R, it is x, y and z. So you will write x, y and z. Suppose these are absolute value. And these are multiplicative. In the property of operator, I have also said that these are multiplicative. So x, y, z, and definitely you can use these also, no issues. When this operator operates, it operates as a multiplication. Okay. Now there will be px, py, pz. So this will be I cap into ypz minus zpy, ypz minus zpy plus zpx minus xpz. If you are not able to understand this, just read from YouTube or Google that how vectors are multiplied, three-dimensional vectors, how three-dimensional vectors are multiplied. You will get it. That's easy. Zpx minus xpz plus xpy minus ypx. Okay, this will be j cap and this will be k cap. Now with the properties of vector, we can actually relate those left hand side and right hand side. We can write Lx equal to ypz minus zpy, Ly equal to zpx minus xpz, and Lz equal to xpy minus ypx. Okay, so in the next page I am writing that. So you can write Lx equal to ypz minus zpy. You can write Ly equal to zpx minus xpz. You can write Lz equal to xpy minus ypx. Okay, just put cap on everything. Okay, sometimes I may ignore this cap, just you have to write that. Okay, now we have to simplify it. We know px equal to minus I h cross del del x. We know px is minus I h cross del del x, right? This is we got this from linear momentum observable, and it is its quantum mechanical operator. Okay, for observable linear momentum, this is the quantum mechanical operator. We know this already. Okay, just if you want to see, I may show you. See, linear momentum, my py equal to minus I h cross del del y. Okay, We have already done this. So we know Px equal to minus IH cross del del x. Similarly, Py will be minus IH cross del del y, and Pz will be minus IH cross del del z, right? Everywhere you have to put just these operators. Okay, now put this value to your mother equation. What we are getting, y into pz means minus IH cross del del z minus IH cross del del z minus z into Py means minus IH cross del del y minus IH cross del del y. No issues. Let's simplify it. Minus plus. Okay, we can write minus IH cross y del del z plus IH cross z del del y. No problem. So we can write minus IH cross, if we take common, we can write y del del z minus z z del del y of 1 second, just take eraser. Okay, fine. Z del del y, we are getting this, and with that you can also simplify it like this. I will not write everything. You can simplify that. If in H cross you can write H by 2 pi, you know. Okay, similarly it will be, finally you can write, if you put H cross in the place of H cross H by 2 pi, then the final equation becomes, and minus if you write 1 by I square, then we can get H by 2 pi I, just do it yourself, y del del z minus z del del y. Okay, and how this conversion, we have done it already in linear momentum. Okay, this portion only. Similarly for Ly, now guess that how these are going to operate. When we are using Lx, see, when we are using Lx, we will always have minus IH cross. This will be always minus IH cross. See, when there is x, we are getting y del del z minus z del del y. So when it is Ly, then z del del x minus x del del z, isn't it? So like this, x to y to z. So when there is x, you will have y del del z minus z del del y, right? When it is Ly, that is basically z del del x minus x del del z. Similarly, if it is z, then x del del y minus y del del x. Clear? No issues? Okay. So till now we have completed angular momentum. We were looking at different properties of commutator, isn't it? See, we have seen four properties of commutator. Sorry. Um, Four properties of an operator. We have seen four properties of operator. Fourth property was saying that classical in every observable in classical mechanics there will be an operator in quantum mechanics, and we have seen that for different uh, observable in classical mechanics like position, like linear momentum, like kinetic energy, like potential energy, like total energy, like angular momentum. We have seen there are operators in quantum mechanics. So what we have in hand now? We have some physical properties. Every particle will have some physical properties. We call it observable. When these physical properties of an particle, that is in classical mechanics, we call it observable. Same physical properties, if they behave quantum mechanically, then there something corresponding to these physical properties, right? Suppose we have energy. Energy is a physical property. Energy is a physical property of a particle. A particle has some energy, total energy or kinetic energy or potential energy. But when in quantum mechanical world, if a particle, for example, it is behaving as a wave, okay, it is in classical mechanics, it is basically particle, and in quantum mechanics this is basically behaving as wave. And in this wave, this is basically the same thing, but it will also have some energy, it will also have some position, it will also have some momentum. If it behaves, we have previously seen there is a duality of particle to wave, right? So in quantum mechanical dimension, if there is a particle, what will be its position, what will be its momentum, each and everything. If we want to extract the value of those things, we need those operators. So we have our weapon is those operators. So to understand quantum mechanical in a very good way, you have to master your weapon. That means you have to remember or you have to recall all quantum mechanical operators I have taught you. Is clear? This angular momentum, you may seem it is tricky, but if you write 3-4 times, 4-5 times, then it will be very clear to you. Okay? And you will be understanding very clearly. Okay? These are not such a tough thing. So fourth property of an operator is complete. In our next lecture, we will be going to fifth property. Okay? Bye bye. Good morning, aspirant. Hope you all are doing well. Your days are